Hello, this is Professor Kuehn, and welcome back to my lectures on space, time, and motion. We're looking at Galileo's dialogues concerning new sciences, specifically his discussion of naturally accelerated motion. We got up to about page 123 in a student's guide through the great physics texts. Here, we see a diagram that represents the distance that an object moves when it's falling from rest. So recall in our last lecture, we talked about how the vertical line ACIO represents a time interval broken into three equal parts, AC, CI, and IO. Then on the line segments BC and FI and PO represent the speeds that the object has acquired after 1 unit of time, after 2 units of time, and after 3 units of time respectively. So for example, in the time segment AC, the object begins at rest, and by the end of that time is falling with the speed bc. In doing so, it will travel the distance that's given by the rectangle ACED, or equivalently the triangle ABC. Similarly, during the 2 second or 2 units of time, the object will have traveled a time interval represented by the line segment AI, and the distance it will have traveled is represented by the 4 rectangles, or equivalently by the triangle AFI, the area of that triangle. And similarly, in 3 units of time, the distance it will have fallen would be represented by the triangle APO. Now, this might look a little bit foreign to you, but I suspect if we turned this diagram on its side, it would look more like something you've seen before. So, for example, if I were to draw velocity on the vertical axis and time on the horizontal axis, t like this, and the velocity, or the speed on this axis, what this is representing is a velocity versus time graph. So if we were to break the time into 3 different moments, so this would be time A, time C, time I, and time O, then after a given period of time AC, the velocity will have gone up to this value right here. And if we take the mean speed, then the distance that an object will have fallen will be the area of that rectangle, or equivalent the area of this triangle. So I'm going to suggestively label this B like that. And now if I draw a vertical line like this line segment, if I label this by an F, then in the time interval AI, it will have achieved a speed of the line segment IF. So I'm basically taking this diagram, figure 9.3, and turning it on its side. So this would probably look more familiar to you as a speed versus time plot on a Cartesian set of coordinates. Of course, the Cartesian coordinate system hadn't really been invented yet, and so Galileo is using this diagram, but it looks an awful lot like a Cartesian coordinate system turned on its side. Okay. Now I'd like to go on to the next pages. So if we look ahead to page 125. Here at the top, Simplicio chimes in and says, "In truth, I find more pleasure in this simple and clear argument of Segredo than in the author's demonstration, which to me appears rather obscure." So in other words, the diagram we just explored on figure 9.3 that Segredo presented us with, Simplicio finds that to be convincing. He goes on to say, "So that I am convinced that matters are as described, once having accepted the definition of uniformly accelerated motion. But as to whether this acceleration is that which one meets in nature, in the case of falling bodies, I am still doubtful, and it seems to me not only for my own sake, but also for all those who think as I do, that this would be the proper moment to introduce one of those experiments. And there are many of them, I understand, which illustrate in several ways the conclusions reached." So in other words, Simplicio is saying, well, if you define uniform motion in this way, I'm convinced that that's the distance that an object would move in a given amount of time. But I'm not convinced that this is actually what happens in nature. So is there some experiment that you can bring forward that would illustrate this? And the answer is yes. And so we go on in the next paragraph, Salviati explains a particular experiment that was done that illustrates this. So how would we draw this? Let me take a moment to draw, he says, a piece of wood. Think about a wooden ramp that looks something like this. Okay, and a ball, let's make it a red ball, that is beginning at the top of this wood ramp. You'll see what I'm doing here in a moment. And this wooden ramp has a groove that is cut into it like this. You might imagine a wooden ramp looking something like this with a groove or a notch cut into it. By the way, you'll be doing something similar to this in lab this week. And suppose it's propped up on some legs, a bit like this. And let's suppose that you were to draw some ticks or some lines on it at various locations. So put one tick here. Let me go halfway down right here, and we'll call this number, I don't know, 6. I'm trying to space these out nicely. And maybe this is 12. Two, 3, 4. We'll see if I get the spacing decently. Not bad. Okay. And let's suppose you were to roll this ball down the ramp and see how far it goes in different amounts of time. So we were to make a table. And we were to measure the distance that the object goes in a certain amount of time. Okay. And let's suppose that in 1 unit of time, it travels a distance of 1. So it rolls down to the first mark in 1 unit of time. And then we were to let it roll down to the 4th mark, so a distance of 4. How much time would it take? Well, it would do that in 2 units of time. And let's suppose we were to let it instead roll down to the 9th mark. It would do so in 3 units of time. And likewise, if this was longer, if I were to let it roll down to the 16th mark, it would take 4 units of time. And so we see that if we do this, the time squared, this time squared is 4, this time squared is 9, this time squared is 16. In other words, Galileo did this experiment. He measured how far the ball rolled down the slotted ramp, and he measured the time, and probably he used a water clock. So how did he measure time? Remember, this is before people had nice stopwatches on their arms. So how would you measure the time? Well, one way that he would do it would be by measuring his pulse. So he'd count how many heartbeats. But that's not a very precise measurement. After all, when you're measuring your heartbeat and you're doing scientific experiments, you get very excited and your heartbeat goes up, and it's not a good clock. So instead, he used what's called a water clock. So how does one set up a water clock? It works something like this. You take a jug and you fill it with water, and this jug has a little spout sticking out of the side, a bit like this. And you put this up on a table, an elevated table, like this. And you fill it with water, and you put your hand, let's say, over top of this, over the spout. And then down here, you have another container. And let's suppose you put this on a scale, some kind of spring scale. I'll draw a little spring down here that measures how much weight of water there is in it. So maybe there's some kind of dial on it, and it measures how much water is in it. And so what you do is you hold the ball at the top of the ramp, and the minute you release it, you take your finger off of this spout, and you let water pour out. And the moment that it gets, let's say, to the 4th mark, let's say when it gets down here to the 4th mark, at that moment, you put your hand back over this, and then you weigh how much water is in this. And you'll measure, let's suppose that you measure a certain weight of water. The amount of water that you weigh is proportional to how much time the water has flowed out. So you're really measuring time in pounds, you might say. So this offers a more precise way of measuring time intervals. And this is presumably how Galileo would have measured these different amounts of time. So he's measuring 1 unit of time it took to roll down 1 unit of distance. It took 2 units of time to roll down 4 units of distance. It took 3 units of time to roll 9 units of distance, and 4 units of time to go 16 units of distance. And in other words, he found that, so Galileo found that the distance it moved was proportional to the square of the time. Okay, so now notice what he's doing here is he's working backwards. In his previous proof, he showed that if something was undergoing uniform acceleration, that is, if the acceleration was a constant, that is, uniform acceleration, then the distance it moves would be proportional to the square of the time. And here, he's working backwards. He's showing that distance is proportional to the square of the time, therefore the acceleration must be constant. So since, in our case experimentally, distance is proportional to the square of the time, then we know that acceleration is constant. Therefore, this ball is undergoing uniformly accelerated motion. So it's kind of the converse of the proof that he has just gone through in this chapter.